Alright, AP Chemistry, good morning to you. You just walked out of taking the Chapter 3 test, and I am recording this video just after you walked out. This is Chapter 4 still, Types of Chemical Reactions. This is the last part of Chapter 4. This is the redox portion of it. Metathesis and redox, really big on the AP exam. This part is section 9 still. We did assigning oxidation states. Now we're just going to go through the characteristics of redox reactions, aka recognizing a redox reaction. Alright, so there are about 5 types of redox reactions, and type number 1, not necessarily in order of, is a combination or a synthesis reaction. You were taught how to recognize these types of reactions. Now we're going to realize that they're redox, and we're going to assign oxidation states and things like that. So a synthesis reaction, two elements coming together to form a compound. If I were to assign oxidation states to this reaction, I would have 0 because it is an element, 0 because it is also an element, it is one of the diatomics. According to the rules of assigning oxidation state, oxygen is a -2 unless it's a peroxide or attached to fluorine. It is neither a peroxide nor attached to fluorine, so this is a -2. There are 2 of them. That's a grand total of a -4. For a compound to be equal to 0, then this guy must be a +4. Now there's something I want you to write down, absolutely, just as recognition. The sulfur element lost electrons. It became more positive. The oxygen gas gained electrons. Notice that it became more negative. Now again, redox reactions are the transfer of electrons. It is bookkeeping. It is just keeping track of how many electrons get transferred. In a redox reaction, something always has to lose electrons. Something always has to gain electrons. Oop. And there's a picture. You did this first year chemistry. This is our sulfur burning. So I'm going to get rid of that so you can write this down. Then I'll bring the picture in again because it was kind of a neat, if you remember sulfur burning in the spoon and it was kind of molten lava. It's kind of neat. Decomposition reaction, which is nothing more than the opposite of synthesis reaction. A compound decomposes either into its elements or to a new compound. So I'm going to do the same thing here. Potassium has a rule. Group 1A is always going to be +1. Oxygen has a rule. It's a -2 unless attached to fluorine, or if it's a peroxide, it is neither, so -2. There's 3 of them, so this is a -6 +1, so right now it's a -5, so this number for chlorine has to be some number. When added to a -5, will add up to be 0, so the chlorine has an oxidation number of +5. -1 +1 and 0. So what I want you to note here is the fact that the chloride ion in the reactant is gaining electrons because it became more negative. From +5 to a -1, it became more negative, so it gained. The oxygen ion in the reactant lost. So it's becoming more positive. It went from a -2 to a 0. And write that down. And a little picture of that. There's a decomposition reaction. Disproportionation reaction, a very large term. Disproportionation reaction are when the exact same element in the reactant side gets oxidized and reduced. So here's an example. If you assign oxidation states to this chemical reaction, this disproportionation reaction, you get a 0. And this whole hydroxide is a -1. This is a -2. The whole thing has to add up to being -1. So -2 plus some number equal -1. That number's got to be +1. This is an ion, so the rules we've already had, so you should know how to assign oxidation states. We did that already. You will notice that nothing changed for the hydrogen here in the oxygen. -2, -2, this would be a -2 and a +1. So that means that the chlorine element, chlorine gas, went from 0 to +1. That is actually going to be a loss of electrons for that, because it's becoming more positive. And it also went from a 0 to a -1. So not only did the same substance lose electrons, but it also gained electrons and became more negative. And you'll notice there's only one reactant and 2 products. That's the usual format. So disproportionation reaction is when the same substance gets simultaneously oxidized and reduced, meaning simultaneously loses electrons and gains electrons. Combustion reactions, we assign oxidation states, and you get a +1 for the hydrogen, a -4, a 0, a -2, a +4, a -2, and a +1. Notice in this one that the carbon loses the electrons. We don't know how many yet. That will come when we balance. Notice it goes to being more positive. It goes from a -4 to a +4. And the oxygen gas, the other reactant, gains electrons. It became more negative. It went from 0 to a -2 and -2 here. Now you don't have to do both of them. I just focus on the CO2 in all honesty because it did the same thing. But you have one that lost electrons and one that gained electrons. So that is a redox reaction. Alright, displacement reactions, which you know as single replacement reactions. And there are 3 types. You have hydrogen displacement. A hydrogen has been displaced by something else. Notice the 2 examples are almost identical. You have to assign oxidation states. Element, -2 + 1. -1, there's 2 of them, so that's got to be a +2. Element, and I'm going to do the same thing here. It looks almost identical. Notice that the strontium has become more positive, so it lost electrons. Notice that the hydrogen, now think about it, if you wrote the water out like this hydrogen gets displaced by the strontium. So one of the hydrogens comes out as its elemental form, goes from a +1 to a 0, so he's gaining. So he's gaining electrons. He is becoming more negative. Now, something I want you to write down that's really important, and we will go over it a couple of different times, once in part 2 of this video, and again in class, so we'll get this down pretty tight. I want you to write this down in big bold letters. Not all displacement reactions work. This is going to depend on the standard reduction potential list, which I'm going to show you in the second video, part 2. So not all displacement reactions are going to work. It'll depend on the standard reduction potential list, which you guys might know as metal activity series. And we will go into that in the second half. Second type of displacement reactions is metal displacement. That's when an elemental metal displaces a metal in a compound. Notice in the first example, the magnesium displaces the titanium, and the titanium comes out in its elemental form. That's super important. The zinc displaces the copper, and the copper comes out in its elemental form. A sign oxidation states +4, element 0, -1, +2. Notice that the titanium ion in the compound went from a +4 to a 0. That means it gained electrons. That means it's more negative. Notice that the magnesium element went from a 0 to a +2. That lost electrons. It became more positive. The zinc, elemental zinc, sulfate, because I know it's going to be the metals, +2, -2, +2, copper's an element, so 0. So again, notice that elemental zinc went from a 0 here to a +2 there. So that means that it lost electrons because it became more positive. And my copper ion in the compound here gained electrons because it went from a +2 to a 0. It's becoming more negative. And again, not all metal displacements are going to occur. What occurs will depend on the standard reduction potential list. So I'm going to write that up here. Standard reduction potential list, which I am going to teach you how to read in the second half of this video. Not all single replacement reactions will occur. Right now, recognize halogen displacement. Halogen displacement is when one halogen, an elemental halogen, will displace a halogen in a compound. So look at the first example. I'm going to assign oxidation states. Element, compound, -1, +1, both have rules. Compound, -1, +1, both have rules, elemental form. Notice the reactant elemental chlorine gas goes from an oxidation state of 0 to a -1. So the element chlorine gains electrons, more negative. You'll notice that the bromine ion in the compound lost an electron because it's becoming more positive. Now, I wanted to show you this one because I want you to write it down so we can look at it when we do the standard reduction potential chart in the second half. And halogen displacement's a little easier to gauge anyway. Again, if I were to predict the products, so I'm going to scratch this out for the moment. If I were to predict the products, I would of course expect to get this as my products. Notice the bromine is in its elemental form. And if you assign oxidation states, you would of course go blindly along and you would say, okay, I'm assigning oxidation states. This is nice and simple. You would say, well, the element iodine is going from a 0 to a -1, so it is gaining electrons and it's becoming more negative. And the bromine ion in the compound is losing electrons. It is becoming more positive, and your theory would be right except for the activity series for halogens, which you're going to go over again. We're going to go over it in the next video. But the halogens are a lot easier than the metal and the hydrogen displacement series. Basically speaking, any halide cannot replace anything above it. So if you were to look at the periodic table and find iodine, you would find that iodine is below the bromine. So this reaction is not going to happen. Poor iodine never gets to replace any of the halides in any of the compounds because, of course, he's at the bottom rung of the ladder. So the displacement series for halogens comes off the periodic table, and you can only replace below you, never above. So that ends part 1.